Maligayang araw everyone. I am Joseph D. Chavez together with Mr. Calvin Pasha, and we will discussing to you the photoelectric effect. First, I will discuss to you what is photoelectric effect. The photoelectric effect is a phenomenon in which electrons are ejected from the surface of a metal when light is incident on it. These ejected electrons are called photoelectrons. It is important to note that emission of photoelectrons and the kinetic energy of the ejected photoelectrons is dependent on the frequency of light that is incident on the metal surface. The process through which photoelectrons are ejected from the surface of the metal due to the action of light is commonly referred to as photoemission. The photoelectric effect occurs because the electrons at the surface of the metal tend to absorb energy from the incident light and use it to overcome the attractive force that bind them to the metallic nuclei. I have an illustration detailing the emission of photoelectrons as a result of the photoelectric effect. And now, let's move on to the topic of Mr. Calvin Pasha. Mr. Calvin Pasha?
Thank you for that, Sir Joseph. So for my part, I am going to talk about classical theories behind photoelectric effect. So it started with Heinrich Hertz, which is a German physicist, when he first observed this effect in the year 1887. So he used a spark gap transmitter in his experiments, which is a primitive radio device. This effect was also known as Hertz effect by that time. And with his experiments, he discovered that upon the absorption of certain frequency of light, substances would give off visible sparks. And these visible sparks were later on identified in the year 1899 by J.J. Thomson as light-excited electrons or the photoelectrons. So the classical picture underlying the photoelectron effect was that the atoms in the metal contained electrons that were shaken and caused to vibrate by the oscillating electric field of the incident radiation. Eventually, some of them would be shaken loose and would be ejected from the cathode. It is worthwhile considering carefully how the number and speed of electrons emitted would be expected to vary with the intensity and color of the incident radiation, along with the time needed to observe the photoelectrons. In 1902, a student of Heinrich Hertz, Philip Leonard, studied on how the energy of the emitted photoelectrons varied with the intensity of the light. So in his photoelectric experiment, in his first setup, he used a high intensity light or a light with high intensity. So it resulted or produced an increased photocurrent, while in his second setup, where he used a low intensity light, it resulted or produced a reduced photocurrent. So in that case, we can say that photocurrent is directly proportional with the intensity of the light. And however, the kinetic energy of the emitted electrons or ejected photoelectrons is independent with the intensity of the light. So take note that it is independent. So it does not depend with the intensity of the light. Leonard discovered that there was a well-defined minimum voltage that stopped any electrons getting through V-stop. So to Leonard's surprise, he found that V-stop did not depend at all on the intensity of the light. Doubling the light intensity doubled the number of electrons emitted, but did not affect the kinetic energies of the emitted electrons. So the powerful oscillating field ejected more electrons, but the maximum individual energy of the ejected electrons was the same as for the weaker field. So that concludes that photocurrent is directly proportional with the intensity of light. However, the kinetic energy is independent with the intensity of the light. Another physicist who works on the photoelectric effect was Robert Millikan. He followed up on Leonard's experiments while using powerful arc lamp. So he focused on the wavelength dependence as Philip Leonard focused on the intensity dependence. So in Millikan's experiments, he was able to generate sufficient light intensity to separate out colors and check on the photoelectric effect using light of different colors. He found that the maximum energy of the ejected electrons did depend on the color. So the shorter wavelength, high frequency light eject photoelectrons with greater kinetic energy. So let us now move on with the quantum theory behind photoelectric effect. So here is the Einstein's quantum picture. In 1905, Einstein gave a very simple interpretation of Leonard's results and borrowed Planck's hypothesis about the quantized energy from his blackbody research and assumed that the incoming radiation should be thought of as quanta of energy hv with v as the frequency. So as you can see the presentation, here is the equation generated or formulated by Einstein. So Ke equals hv minus phi. Ke here stands for the total kinetic energy, which is equals to hv, wherein h is the Planck's constant with a value of 6.62607015 times 10 to the negative 34 power meter squared kilograms per second. So that's the value of the Planck's constant. And v is the frequency minus phi. So phi here stands for the work function, wherein work function is the amount of energy required to remove an electron from an atom or molecule in the gaseous state. So in some cases, in some references, this formula is equals to Ke is equals to Hf minus phi. So wherein yung F is the frequency. So the equation of Einstein explains the properties of the photoelectric effect quantitatively. A strange implication of this experiment is that light can behave as a kind of massless particle now known as photons, whose energy E is equals to hv, which can be transferred to an actual particle which is an electron, so impacting kinetic energy to it. So Robert Millikan initially did not accept Einstein's theory because he saw it as an attack on the wave theory of light. And after 10 years of working or studying it further, so until 1916, that was the only time that Robert Millikan accepted this theory of Einstein. So imagine 10 years had passed before he accepted Einstein's theory. So Einstein's simple explanation completely accounted for the observed phenomena in Leonard's and Millikan's experiments and began an investigation into the field we now call quantum mechanics. So this field seeks to provide a quantum explanation for classical mechanics and create a more unified theory of physics and thermodynamics. The study of the photoelectric effect has also led to the creation of new field of photoelectron spectroscopy. So Einstein's theory of the photoelectron presented a completely different way to measure Planck's constant than from blackbody radiation. So presented here is the comparison between classical physics and quantum physics about photoelectric effect experiments. So in classical physics, with regards to the threshold frequency, an incident light of any frequency can eject electrons. So it means that it does not has a threshold frequency as long as the beam has sufficient intensity. While in quantum physics, to eject an electron, the incident light must have a frequency greater than a certain minimum value. So there is a threshold frequency. So no matter how intense the light is. So when it comes to maximum kinetic energy of photoelectrons, in classical physics, it only depends on the light intensity. While in the quantum physics, it only depends on the light frequency. So, in the emission of photoelectrons in classical physics, there should be some delays to emit electrons from a metal surface. While in quantum physics, electrons are emitted spontaneously. So, there are no delays. So, when it comes to the energy of light in classical physics, it only depends, once again, in the light intensity. While in the quantum physics, of course, it is only dependent on the frequency of the light. So, therefore, we can conclude, or with these conclusions and results, this only proves the duality of light, wherein a light can behave as a particle and also it has a behavior of a wave. So that's all for our report. Thank you for listening and God bless us all.